Hello, 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 hello. This is Arnapati, and I welcome you to the very first episode of our itihaas podcast. Now, given this is the very first episode, I'd like to give some disclaimers. Number one being the fact that the whole idea behind this podcast is to make it a discussion, a conversation regarding history. Now, in this, we will be following a broad timeline, the same linear historical timeline that we see being followed in most of the history books, from ancient, medieval, modern. But at the same time, it will be, like I said, more conversational in nature. It'll be impromptu, even though in every episode will be like a broader topics that we'll be covering based on wherever we are in the timeline. The second thing being that given that this is going to be an impromptu conversation, there might be certain disruptions, but I hope it doesn't distract you as much as it distracts me sometimes. And then lastly, whatever sources, books, paper that I would refer to, I will put them down in the description of the podcast itself. So if you would like to check them out, or if you want them, you will be able to go ahead and take a look at by yourself as well. Now, also, if you want to get in touch with me, there's a Telegram channel where I'll be sharing these sources periodically, as well as my email address will also be there in case there are any inputs you want to provide me regarding this podcast or any upcoming podcasts. So with that out of the way, let's begin our very first episode. Now, this episode is very similar to how I would approach teaching history. In all the classes that I've taken, especially the very first class when I take regarding history, and given that most of my students are Indian, I ask them this question, what is history? What is history for them? And the very first answer that you would get would be the timeline, the whole idea of ancient, modern, medieval history and those events that happened during those times is history for them, right? And I don't fault them. I mean, they are right by their own perspective, because at the end of the day, if you see the Indian textbooks, most of them follow the same idea of ancient, medieval, and modern history. And this classification of events that they read in these books is what is history for them. So, what's wrong with that? I feel like the only small addendum that should be present in these books is the fact that history has two facets to it. The very first facet being the events that did occur in history, how they happened, where they happened, what are the causes of them happening. But the second facet is as important, which is the person who's telling you about the first facet, the person who's narrating you these things, the person whose perspective you're seeing the history from, right? So a quick Google search of what is history would tell you that history is nothing but a record of past events, or events which are particularly related to human affairs, and that's what history is. But they never talk about the fact that the person who narrates history, the person who writes history, they are also trying to interpret it from their own knowledge, right? From the evidences they had. And that's how I see history. That's how I tell them to sort of start viewing history, because a lot of times you don't get both sides of the conversation. For example, as a broader example, let's say we talk about the First World War, right? And the First World War will then have both sides. So history would be written from both sides, the side of the loser and the side of the winner. Now, this same perspective can be given to any of the historical events that have ever happened. A really good example of this was when the colonialists, when the British people, when they came to India, the East India Company people, they started researching about Indian culture and heritage. And a lot of them had this hidden agenda of proving their superiority, right? So to do that, a lot of times they would form narratives that would support the claim that, say, India has always been under subjugation, or that India has never been civilized, or other any sort of conversation that would help their agenda, right? So at the end of the day, this is what history is. History is the events that have occurred and the person who is talking about those events, right? And ironically, I am one of those people who is talking about those events. So again, this perspective of history that we are about to see, you are going to see it through my eyes and my conversations and my perception. So again, I would say that none of this is completely infallible. You can go ahead and check for yourself. You can go ahead and cross-check the things that I'm talking about, and we can obviously make this into a conversation. And that's the whole idea. So yeah, coming back to the whole beginning of history is understanding that history has two facets. The first facet being the events that occurred, and the second being the person who is narrating them. Now, going from there, walking a little back, the main question of where does history begin is also another important factor for us. For example, if we start talking about history and we start chunking it into this whole idea of ancient, medieval, and modern, you would see that the ancient time period somewhere starts around 6000 BCE. Now, again, this is an arbitrary time period taken by some books. Some say that we can begin the ancient history at 10,000 BCE. Some go farther back, some go farther forward though. But I would suggest that if we have to look into history, for us to even come till that point, for us to come till, let's say, 10,000 BCE, it is important for us to see what happened before that. Because again, what is history? History is a study of past events. So again, when we are talking about past events, I say let's go farther back. Let's go farther back, not only towards the evolution of human beings or even evolution of animals or evolution of the very first single-cell organism. We go even farther back to the beginning of Earth. I think that is a very good point for us to even start talking about history. Now, again, when we start talking about the beginning of Earth, we are essentially talking about the Big Bang and the billions of years following that till reaching Earth. So let's say if the Big Bang happened around 3.8 billion years ago, the formation of Earth or the Earth's age is somewhere roughly around 4.567 billion years ago. So this time scale is the time scale we'll be following. But the only disclaimer here being that if we start going into the beginning of Big Bang, things get very complicated and you can make countless episodes on just that beginning part. So I am just going to sort of breeze over it. I was reading this book called The Story of Earth by Robert M. Hassan, and he explains it beautifully, the whole mystery around Big Bang. He says that the stage was set for our planet's birth much earlier at the origin of all things, which is the Big Bang. About 13.7 billion years ago, by the latest estimates, that moment of creation remains the most elusive, incomprehensible, defining event in the history of the universe. And I love this line that follows after that. He says that it was a singularity, a transformation from nothing to something that remains beyond the purview of modern science or the logic of mathematics. And if you would search for signs of a creator, a god, in the cosmos, the Big Bang might be the place to start for it. And that's exactly how complicated the Big Bang is, because the idea is that the concept is beyond the ability to craft metaphors around. You see, our universe did not certainly appear where there was only vacuum before, because before Big Bang, there was no vacuum. There was no time. Our concept of nothing implies emptiness. Before the Big Bang, there was nothing to be empty in. So the whole idea of Big Bang is very elusive in that sense, because from nothing, we didn't go to something, we went to everything. So everything that we see today came from that nothing and just became everything, right? So again, very complicated, a little more in-depth for us to cover in this podcast. But let's just say the Big Bang happens, and as the Big Bang happens, we move on to the formation of Earth. Now, the formation of Earth is again a story of gravity and a story of how this big ball of dust clumped up together around this newly born star and formed the planet, right? Now, there is a big gap between 13.7 billion years to, let's say, 4.6 billion years where we start talking about Earth. And in that gap, we see a lot of stars forming, a lot of stars dying. The atoms, the molecules that we see today also come from this time period where we see, because as it was theorized, that in the very beginning of the Big Bang, it was mostly hydrogen. Hydrogen was more than 90% of all atoms. And there was a few percent traces of helium and traces of lithium thrown in there, but that slowly coalesced, that became suns and stars, and then they gave birth to more and more elements. So fast forwarding to that, we reach a point where the Earth is now beginning to form. And the formation of Earth is again a really amazing story in itself, because what happens is you find small particles coming together, coalescing because of gravity. Now, gravity is the most defining factor, the most defining force for our whole universe. So as masses increase, masses clump up, they attract more masses. And what happens is, as the Earth forms, the heavier, denser elements start moving towards the center, and the lighter elements stay around the core. And that is how Earth was formed. And this formation did not take very long. In the grand scale of things, if you look at it, the formation of Earth only took about 20 million years. The very first, like this, the grains clumping up together, colliding, growing to form the very first protoplanets. That just took about 20 million years, which is a blink in the geological timescale. I mean, think about it. We're talking about billions of years, and 20 million years is nothing. So during this time, the Earth was a hot mess, and it was battered by a rain of impacts from other protoplanets and asteroids, which kept most of the surface molten, right? And this is where basically the Earth begins. Now, before we dive into these periods, what happens, the reason why I'm talking about the beginning of Earth is because there's something known as the geological timescale. The concept of trying to analyze this whole timeline from 4.6 billion years ago till today, categorize it into different eons and eras and epochs and ages, so that we can understand the time better. And this geological timescale is what helps us sort of understand this huge timescale, which is very difficult for us to imagine. Now, the idea of the geological timescale is quite new. The whole idea of studying rocks, geology or stratigraphy was something that was, I would say, a brainchild of Nicholas Steno, who first wrote the laws of stratigraphy in 1669. He published a book about these laws where he said that we should look at the layers of Earth, and he hypothesized that the layers closest to the surface are younger or newer layers, and the layers going below are older and older layers. And this idea of looking at Earth's age through the layers was very new, because imagine during this time we are still questioning about how the Earth moves, if Earth is the center of the universe or not, and things like that. So coming up with such a brilliant idea during a time like this was something really revolutionary. Now, people started building up on that idea, and finally Giovanni Arduino, around the 1760s, when he was studying the Italian Alps, he started hypothesizing that the very lowest layers are made up of the metamorphic and volcanic rocks should be called the primary layers, and the one above that with the hard sedimentary rocks should be called the secondary layer, and then the softer alluvial deposits would be called the tertiary or quaternary layers. And then this was further built up on by William Smith, who in 1819 finally spoke about something very logical. He said that what Arduino said, that we should divide these layers based on where we find what rocks, had one problem with it. The problem being the fact that if I'm going up a mountain and the type of layers and soil that I find there is going to be very difficult or different to what I find on a plain. So how do I compare? Basis on what do I compare which layer is what, right? Because see, the idea is as you go deeper, you should find older and older layer of things. But a mountain being at a height, what is depth in there? How do you consider the depth? So, and how do you compare different layers from different time scale? Is digging a kilometer at Everest the same as digging a kilometer down in the Deccan Traps? Will it result in the same timeline? So questions like these started popping up, and then finally William Smith in 1819 said that, why don't we compare the fossils that we find in each layer? Because the organisms that might have existed in that layer would have existed at a particular time period. So if all the fossils, let's say, existed at that time period, wherever that fossil is found, at whatever layer it is found, we can conclude that that layer is going to be same throughout the earth. What I'm trying to get here is that, for example, let's say we find a layer of trilobites. So and then on top of that, we find a layer of ammonite fossil. So knowing that trilobites were evolutionarily, they happened before, they came before the ammonites, we can say that wherever we find the trilobite layer is going to be below the ammonite fossil layer, and wherever that trilobite layer is will belong to a particular time period. Now, it's a lot to wrap your brain around, but the whole idea here was that they started looking at the geological timescale based on the fossils and started dating it based on the fossils. Now, as we will go forward and start looking into this a little deeper, we'll find that there are certain fossils which became key fossils for particular layers. There are very particular defining factors. In fact, there are a lot of times that are where there are geographical events, for example, the freezing up of Earth or the thawing of Earth, which happened all around the globe and can be kept track of through these layers of soil itself, through the layers of depositions itself. So that's how we came about the whole geological timescale. Now, the reason why I mentioned the geological timescale here is because what we're about to do from the very beginning of Earth to as we go towards, let's say, approaching ancient history, approaching that 10,000 BCE mark, we'll see that this time period from 4.6 billion years ago till, let's say, 10,000, 20,000 years ago has been divided into these geological timescale for us to understand it properly. Now, there are bigger divisions and subdivisions in this geological timescale. The biggest divisions are called eons, then followed by eras, periods, epochs, and ages. Now, eons and eras are really big timescales. Here you could see jumps of about 500 million to 2 billion years, whereas periods and epochs help us understand more minute timescales, and they become much more frequent as we come towards the present time. That's because by this time we see evolution really pick up pace, and we see how different organisms start to react. So we go from no life on Earth right from the beginning, remember when we were talking about the formation of Earth, to the coming up of some biological life form, to the evolution of the very first single cell organism, then multicellular organisms, and to the complex living organisms where we are today. So that's the whole idea of the geological timescale. Now, the geological timescale begins with the Hadean eon. The Hadean eon is important for us because this is the time period where we talk about the formation of Earth, and a lot of big events happen during this time period. This is also the time period where we see the moon forming. But before we reach there, let's talk about the Hadean eon a little bit. Now, the Hadean eon is named after the Greek god of the underworld Hades, because in that Western concept of hell, which talks about a place which is just in fire, enveloped in fire, it's burning hot and there is no life at all. That's exactly how Earth was 4.6 billion years ago. That's the Hadean eon. That's how we named it the Hadean eon, because it represented the underworld, right? So during the Hadean Eon, we come across an Earth which has a surface temperature of over 200 degrees Celsius or 390 degrees Fahrenheit. And at this time, there was no oxygen. There was almost no oxygen. There was lack of ozone layer, which meant that the Earth was being flooded with the deadly radiations emanating from our sun. And during this time, the Earth was also being bombarded with a lot of asteroids. This is also the time where the Earth is so hot that there is no stable crust. Things are moving, tectonic plates are still moving, and during this time, one full rotation of Earth was only 4 hours long, which gradually lengthened to about 10 hours by the end of Hadean Eon. Now, this is also the time when the sun was only 70% as bright as it is today, and this is also the time when we see the formation of moon. One of the other distinctions that we get during this time period when we look at the geological time scale would be the word Precambrian and Cambrian. Now, the reason Precambrian is not being referred to anymore is because, as the name suggests, Precambrian era was seen as the era before which life was present. Whereas now, from the latest researches, we've seen that there are evidences that by the end of Hadean Eon, it probably was possible for us to have some sort of organic life form, because we have found traces of organic carbon. Researchers have started calling it Luca, the last common universal ancestor, and it is said that from it all life on our planet evolved. It probably began through chemical reactions that preceded simple organic compounds, including the building blocks of life. And this Luca can be studied using the genomes of living fossils or living species, including single-celled organisms. But the whole idea of Precambrian and Cambrian doesn't really hold a lot of weight anymore, given that there have been evidences that we could have had very simple organic life come on by the end of Hadean Eon. Now, during this Hadean Eon, we talked about or we mentioned the formation of moon. Now, our planet's moon is thought to have formed when another protoplanet called Thea, it collided with Earth around 4.4 billion years ago. The collision, very recently I saw this animation on NASA's website. I'll try to link it in the description of the podcast, which simulated the collision of the protoplanet with Earth, and it almost was like fluid dynamics, where you would see two big giant planets colliding with each other, with a lot of mass being left out and a lot of mass being thrown into the orbit, and then that mass and a big chunk coalescing into forming the moon. Now, a huge part of Earth would have melted, vaporizing rock and existing water. Where did this existing water come from? Theories suggest that a lot of asteroid impacts during that time would have had water in it, and with this, with the impact of Thea, onto Earth, a lot of this existing water must have evaporated and formed the very first atmosphere as they condensed, leaving behind CO2, hydrogen, and water vapor. Now, back then, the idea was that the impact of asteroids would happen periodically throughout time, but initially the Earth's gravity wasn't strong enough, but slowly it became strong enough to a point where it could hold on to its own atmosphere. Now, this impact with Thea perhaps was the most important event in our planet's early history, because it may have nudged Earth, causing it to tilt on its axis. This 23-degree tilt that we see, which produces our seasons, and as the high latitudes periodically turn towards the sun, as well as if this collision didn't happen, we wouldn't have the tides, because the tides are again found with the moon. And this whole collision, which ejected this chunk that became the moon later, which started slowly drifting away from us, is technically still drifting away from us. The moon is still drifting away from us at a rate of around 4 centimeters per year. And this is happening because of, again, the interaction of the moon's gravity with our oceans, which is the tidal wave motion, as well as the initial ejection that happened. And it has been theorized or calculated that as the moon departs, our planet's days will lengthen by about 19 hours every 4.5 billion years, which is, again, a very large time scale. But yeah, so that's how moon basically was formed. Now, from this point onward, as the moon was forming, the Earth was also starting to cool down a little bit. We see that the water that was coming in from these asteroid impacts and that was there on Earth starting to condense and cool down. Oceans are the cradle of biological life, but they did not always exist, and this is where it sort of begins. See, despite the temperature on Earth's molten surface, the intense atmospheric pressure prevented the early oceans from evaporating. However, the water was lost to space more easily due to the smaller mass of our planet, which meant molecules could escape Earth's gravitational pull. Now, slowly, this became better. And by 4.4 billion years ago, the Earth had cooled sufficiently for more permanent seas and rainfalls to happen. Our ocean now, at that point, covered 71% of the planet's surface, and water was incorporated into minerals within the Earth's crust, mantle, and core. So that is where the Hadean eon sort of ends, and we step towards the Archean eon. Now, the Archean Earth was an ocean world. The seas were hotter than a bath, and it was tinged green, and the atmosphere was full of poisonous gases, and the surface temperatures were still hot. Microbial life started flourishing during this time, releasing the very first breath of oxygen, because we start seeing photosynthesis happening, and it would still be, from this point, it will still take about 1 billion years before complex organisms come about. So, for 1.5 billion years, the Earth remained a harsh environment for life, and the Archean rock formation, dating between 4 to 2.5 billion years old, still exists, but are often heavily metamorphed, having been heated over eons and folded repeatedly. So the idea of studying rocks and trying to understand how old rocks are doesn't always really bore a lot of evidence, because almost all the rock from that time period, from the Hadean or Archean era, at this point has been either recycled, eroded, or metamorphed into new rocks. But still, there have been certain discoveries of really old rocks which have been possible through zirconium dating, which we'll talk about later. But yeah, coming back to the Archean eon. Now, with Hadean eon, we saw that Hadean starts from 4.6 billion years ago till 4 billion years ago, and then we mark our Archean eon at from 4 billion years ago to 2.5 billion years ago. Now, as you would see, the timeline doesn't really match up. It's not a uniform timeline, and then that's because the geological timescale is not divided into uniform time periods. The divisions in our geological timescale are based on some really huge events that mark the beginning or end of something big, right? For example, the reason why we move from Hadean to Archean at that 4 billion years ago mark is because a lot of huge changes happened during this time period. The first one that we should talk about is something known as the late heavy bombardment. As the name suggests, late as in being late into the formation of Earth, and heavy being a huge number, and as the name suggests, bombardment means basically the bombardment of asteroids coming in and impacting on Earth. Now, the reason that it is significant during this time period is because as you would see, by the end of Hadean eon, the temperature of Earth had started to cool down. The crust was cooling down from being a hot, big giant ball of magma to having a cooler surface temperature. And during this time period, the bombardment that happens right at the end of this basically kickstarts the formation of water on the Earth's surface. Now, here we're not talking about the fact that just from this point of time, water starts coming into being, but more like this is what makes the planet appropriate to hold on to its own water. So what happens basically is the story of water coming to Earth or water originating in Earth is again a little complicated, because as a lot of research went into this, researchers found that the water that is present on the Earth's surface can be accounted by either the asteroids that came in, because these carried water in them. Now, we're not talking about them being just big chunks of ice, but they did have compounds, like the chondrite meteoroid was made up of water. It did have hydrogen in it. It did have heavy hydrogen in it, in fact, which later on made water. And then there is also a lot of speculation about similar impacts happening and giving water on Earth. Now, again, the reason why I'm calling it complicated is because there is a debate about heavy water and light water and how that also changed, and how the solar winds kind of helped catching light or hydrogen and making the water. But we don't need to go into that much of details. All we need to know is during this time period, the temperature of Earth was hot enough to extract the water from these meteoroid impacts that was happening on Earth. And slowly, as the Earth cooled down, it started keeping the water in its own surface. Now, before this time period, the atmosphere of Earth was also mostly just toxic gases. As we saw, that the atmosphere of Earth would have carbon dioxide, methane, and other atmospheric gases which are obviously not conducive to Earth. And in fact, if you look at it closely, methane, ammonia, carbon dioxide, all these are greenhouse gases. If you've read a little bit of geography or are aware of this, them being greenhouse gases basically means that they do a really good job of trapping the heat that comes from the sun. And during this time period, as the Earth was still cooling down, the water should have been evaporated, because the temperature of Earth was still very high, around 230 degrees Celsius by the end of Hadean. But the reason why it did not evaporate is because the atmosphere was so heavy that it would keep the water in its liquid state. Now, this is a really cool experiment that has been done in many ways, where you would see that the temperature at which the water boils changes with the atmospheric pressure. For example, if you boil water here at a normal sea level, the water would be boiling at 100 degrees Celsius. Whereas if you go, let's say, on Mount Everest, on top of Mount Everest, where the pressure is 1/3 of what it is at the sea level, the water boils at 68 degrees Celsius. The reason being that the atmospheric pressure there is low, so the water is able to boil at a lower temperature. So the reverse happens during the end of Hadean, where the atmospheric pressure is around 215 bars, which is about 215 times of the atmospheric pressure that is now today. Because of such high pressure, even at high temperature, the water was still at a liquid state. Now, as we cross over from the late heavy bombardment period and start entering the Archean period, Archean, which is a Greek word that means beginning, we start to see the beginning of life happen. So an experiment was done during this time period to see exactly how life would form in such hellish environment, because as we remember, the atmosphere is full of carbon dioxide, methane, ammonia. There's not really a lot of oxygen available. So how does life form during this time period? So the experiment that I'm talking about is also known as the primordial soup experiment, which was basically what the scientists did was they simulated an environment of carbon dioxide, methane and ammonia, and passed a lot of electricity through it. which resulted into the formation of amino acids, which are basically the building block of life. Now, if you ask where did we get electricity or lightning during that time period, well, at that time period the atmosphere was full of charged ions and the lightning was everywhere. So these amino acids started to form, and at some point in during this time period, one amino acid happened to go down to a vent in this soupy, watery earth and got encased into a layer of fat, which ended up creating the very first living cell. And that is where the story sort of begins. Now, in the Archean Aeon, as the temperature started to cool down a little bit, what started happening was these small microbial life started coming in. Now, during this time period, when I say water or make any references to water, I'm not talking about the water that we have today. During that time period, the water on the Earth's surface was almost lime green in color, and that was because of the high presence of iron mixed with sulfates, and these ions made or iron compounds made the whole water green in color, greenish in color. Now, the reason why that color is important to us is because what happens next. Because during this time period, as the globe was starting to cool down, the average temperature was reaching somewhere between 50 to 85 degrees Celsius. We start seeing something new happening. Now, like I said, these amino acids were forming, they were becoming these small cells, and these small cells needed some sort of energy to sustain themselves. Now, most of these cells were sustaining themselves through chemical reactions, what we know as chemotrophy. Because during that time, no light would reach the seabed, but chemicals dissolved in the water could sustain a small but surprisingly complex food chain of microorganisms during that time period. So these were chemotrophs, they were eating the chemicals. Now, during this time period, some amazing chance of happenstance, amazing evolutionary, whatever you may call it, what happens was, one of these organisms starts coming up to the surface of the water and slowly starts reacting with the sunlight it was getting. Now, and imagine this is happening in a scale of 1 billion years. So the nature had, I mean, it's still very early to call it nature, so let's call it proto-nature. The proto-nature had its own way, of experimenting with a lot of things. And one of the experiments that happens during this time period was this little organism trying to experiment with sunlight. And that's what happens. It reacts with sunlight, it breaks it, and with the help of water and CO2, it breaks it down and produces energy for itself and gives out oxygen as a byproduct. Now, this process gets repeated by multiple cells, and this is where basically the building blocks of photosynthesis occur. Now, a very cool question that comes into mind during this time period when we talk about this time period is, how do we know about these things? How did we actually figure this out? Yeah, sure, we did a few experiments, but how did we know that this is exactly what happened? Now, obviously, it's very difficult for us to construct a time machine, go back in time and look into it. But what we can know is the type of carbon that we have today, the carbon that makes up all the organic life, which is also known as carbon-12 or biogenic carbon. The moment we start finding traces of this biogenic carbon is when we see that life form was sort of coming into existence. And when we start looking into the stromatolites or other fossil remains of this time period, we find the traces of biogenic carbon. Now, the reason why biogenic carbon or carbon-12 is important to us is because carbon does have a lot of isotopes. Carbon has carbon-12, carbon-13, carbon-14, but as the name suggests, carbon-13 and 14 are heavier in nature, and that's why most of the those organisms during that time period could easily consume carbon-12 as compared to carbon 13, and the ratio between carbon 13 and carbon 12 is the ratio that we find. The ratio that we find today is the same ratio we start finding during that time period, and hence tracing this biogenic carbon is what tells us that yes, there is some sort of organic life that has come into being. Now, going back to our timeline, like I said, that during this time period, phytotrophic or sun-loving, photo-loving microbial life forms have started to come into existence, and we start seeing that the atmosphere during the Archean period, which is so rich in carbon dioxide, which is so rich in methane and ammonia, is now going to slowly change, because these phytotrophic microbial life forms will start taking up more and more carbon dioxide and giving out oxygen. And these are nothing but cyanobacteria. These are the cyanobacteria which laid the foundation of life and laid our next step into our evolution, which is the Proterozoic era. Now, the Proterozoic era is basically the beginning of life. It's where the life and the evolution will now really kick off. Now, this Proterozoic era is marked from 2.5 billion years ago till 541 million years ago. Again, these are not arbitrary numbers. They will be marked by some big events. Now, as we start moving towards a Proterozoic eon, we will come across something known as the Great Oxygen Catastrophe. Now, as the name suggests, the Great Oxygen Catastrophe basically means it marks one of the biggest extinction events of life on Earth, even before life, life as we know the complex life even began. Because what happens during this time period is that these cyanobacteria, they start consuming a lot of carbon dioxide out of the atmosphere. Now, like I said before, during this time period, alongside these phototrophic organisms or these phototrophic cyanobacteria, we also have chemotrophic life forms which are consuming a lot of chemicals and things that are dependent on the CO2 that is there on the atmosphere, which is now being used by these cyanobacteria. Now, because of this, a lot of these cyanobacteria will keep on consuming the carbon dioxide that is there in the atmosphere, and there'll come a stage where the carbon dioxide will completely be depleted, the oxygen will fill up the atmosphere, and there will be a complete saturation of the atmosphere with oxygen. And that changes things. That really changes things, because remember the lime green color of the oceans we were talking about? Well, those lime green color were happening because of iron, which was still in a non-reacted state because there was no oxygen. And you know what happens when oxygen reaches iron? There is formation of rust. The ferrous oxides are formed, and that is the reason why during this time period, during the Great Oxygen Catastrophe, the whole oceans of Earth, this proto-Earth, will turn orangish red because of this. Most of the organisms which depend on CO2 won't be able to get it, and that's the same fate that a lot of these cyanobacteria will also suffer, because they would reach a point where they've consumed all the carbon dioxide and there is no more carbon dioxide to be found. So as you can see, this is all leading towards a catastrophe, and that's what the Great Oxygenation or the Great Oxygen Catastrophe is about. Now, another thing that you have to keep in mind during this time period is the fact that, like I said, the CO2, the methane, the ammonia, the sulfur oxides which were making up the atmosphere during that time period were greenhouse gases. They were keeping the temperature of Earth at a good, nice, warm temperature between 55 to 85 degrees Celsius. Now, as all of the carbon dioxide gets consumed and then the methane is also getting broken because of the oxygen, all of these greenhouse gases will disappear, and suddenly the whole atmosphere that was keeping the Earth warm will again not be there anymore, which will lead to a complete glaciation, which is also known as the Huronian glaciation period. Now, this again is the beginning of the Proterozoic era. So all was not lost. It's just that I find it remarkable that for us to be who we are and for how the evolution has happened, it has gone through a lot of dramatic changes. And yeah, we will keep covering these dramatic changes in our next episode, where we will talk about the Proterozoic Aeon and then slowly reach towards the Cambrian phase. And let's not forget the whole theory of human evolution, the Darwinian evolution, and how chimpanzees have come from how humans have come from chimpanzees rather, is something that has been interesting. A lot debate has happened on it. So that's again something that we'll talk about in our next few episodes. So again, thank you so much for tuning in. Thank you so much for listening. This has been the very first episode. Episodes will usually last about an hour, or sometimes a little more than an hour. But yeah, let's keep this at a comfortable pace. I hope you're enjoying this. And if you have any doubts, any questions, you can reach out to me in the socials that I mentioned in the description of the podcast. Again, thank you so much. Subscribe if you love it. And these podcasts will keep coming out on a weekly basis. Thank you so much. And I'll see you in the next episode. Bye-bye.